All right, let's get started today. So this video is going to be a kind of a lighter introduction to Feynman diagrams. Subsequent videos will go into kind of the more hardcore versions, including a lot more of the rules and definitely the actual mathematics that lie behind the Feynman diagrams. But for now, we're going to introduce the basic concept, how to draw them, how to be able to interpret them conceptually, what are they showing, and a few of the rules that are necessary that'll get you by most things. And like I said, next time we'll start looking at what the Feynman diagram actually means, how you translate it into integrals and things like this to actually do calculations. So the first thing to note is what the heck is a Feynman diagram. Of course, if you've seen any particle physics-y stuff before, you've seen things that kind of look like this. You've got a line, some kind of squiggle, and then a line and a line, something like this. Maybe you have arrows. E minus, E plus, gamma, E minus, E plus, let's say. So this is an example of a basic Feynman diagram. And the way to interpret this, basically what it is a visual model that will help explain some interaction between particles. Okay? What we're going to find as we go deeper and deeper into the subject is that what seems to be just a basic interaction, here for instance, this is an interaction between an electron and a positron, so matter, antimatter, annihilating to create a photon, pure energy, and in that photon then, all that energy becomes a pair of electron and positron again. So very basic, we understand this, we know matter, antimatter annihilation occurs, and this is just a visual picture to show that interaction. The problem in real particle physics is that this interaction is not so easy, it's not so simple as what I've shown here, because this is a simple way for this interaction to occur, but it's not the only way for this interaction to occur. For instance, one thing that could happen is as this photon is going along, after it's been created from the annihilation, it right here can create another electron-positron pair, like this. Maybe this is the electron, this is the positron over here. And it comes back together to create another photon, and then that photon then again disintegrates and creates an electron-positron pair. And then each of these loops, or you could have another interaction, maybe an electron sends a photon to this positron over here. Before the interaction occurs, I mean, obviously, they're being attracted to each other because it's a negative and a positive charge. And so maybe they're getting closer, they feel a force, the Coulomb force, attracting them to each other. And of course, that's mediated by the photon. So maybe a photon is sent from the electron to the positron to say, hey, come on over here, get closer to me. And of course, you could have the same over here. You get to include all sorts of extra stuff that could be happening during this interaction, and each one of these can have some probability of occurring. If you have an actual electron and a positron that are coming together to annihilate to create a photon, and then that photon again creating an electron-positron pair, it may be most likely that the basic interaction occurs without all these extra things, but then there's some likelihood that maybe an extra interaction, an extra photon is sent between them, and then maybe even less likely that as the photon's created, it creates a temporary electron-positron pair and then comes back together. Each one is possible, and this is the thing about particle physics, if the interaction is possible, then it's included in the calculation for how likely a particular interaction is to occur. Of course, what we're doing is we're looking at what did we start with. We started with electron-positron pair. What did we end with? Electron-positron pair. And there was some interaction prior, in the middle of this thing. And we don't really care too much about this, intermediate steps, what's actually physically going on, what are all the huge details involved. We just care you had electron, positron come in, annihilate, create a photon, and then that photon again created electron-positron pair. That's the main thing. And we're trying to figure out how likely is it that this happens. That's collision amplitudes or things like this. If I were to send these particles close to each other, how likely is it that they will interact in this particular way and give rise to these results? That's all I care about. And the most probable interaction, as is true usually in life, is the simplest one. The simplest one is the most likely to occur. But these more complicated ones can also occur. And so, because they can also occur, you have to add them into your calculation for the probability of something happening. And so, what's nice about Feynman diagrams is that it gives us an easy way to figure out what are all these extra possibilities that could occur, because it's easier to visualize them than to just kind of sit down with mathematics and write down an integral that'll tell you every single possibility in the universe. It's much easier to draw a picture and then say, okay, well, how can I mess with the picture using particular rules and come up with every way you can mess with it. And each time you draw the picture with one of these new ways, just be able to read directly off the picture what are all the terms I have to put in my integral. It's very, very nice for this kind of stuff. And it turns out, of course, that there's going to be an infinite number of ways any particular interaction can occur, because I can always, look into this photon right here and say, well, at this photon, it too can create an electron-positron pair that has its own interaction. And then I could dive deeper into that little bitty interaction and say, before they come back together to annihilate again, maybe the electron sends a different photon to the positron to say, hey, you need to get closer, and all this kind of stuff. You could just keep adding more and more and more complexity. So this could go on for infinity. This could just happen forever. But because the more complicated the picture gets, the more pieces there are involved, the less likely that interaction is to occur. You're basically going to be summing up infinite series, like you do in Calculus 2 and Calculus 3, and we know that it's possible for some infinite series, or infinite sums, to be able to converge to a finite number. So you say, well, wait, if there's an infinite number of ways these two particles can interact in this particular way, is the probability infinity? Well, no, because the main way may be like, it's a 30% probability this thing's going to occur. And if it's 30% for the simplest way, and each other way, yes, is slightly less probability, but you're still adding more probability in, well, it might be that the 10th order or the 50th order correction term, it's called, gives rise to such a small fraction of a percentage that it's not really going to diverge anymore. It'll still converge to a set percentage, a set probability. And that's kind of the magic that's involved here, that we can take what seems to be infinite complexity and be able to sum it all up into a set of pictures we can draw. And even if we don't want to draw every single picture, because we can't since there's an infinite number of them, by starting to draw the first few, you will see a pattern develop. And from that pattern, you could do the mathematics a little bit more easily with intuition, rather than purely, I have to draw an infinite number of pictures now. So that's kind of the theory behind Feynman diagrams. Let's look at some of the rules of drawing them appropriately. The first thing to note is there's what's called a primary vertex, the fundamental vertex, which is you'll have three things coming in to a vertex. Okay, so that's your vertex. You got some particle A, some particle B, and some particle C, and they all meet at this vertex. Now, the way to read Feynman diagrams, unfortunately, when I was a student, the professor I learned particle physics from, he was an older guy. He was retired and everything at that point. And when he learned particle physics, they had a different standard, or at least the standard was not yet set, as it is more set today. And that is with your axes. We're basically drawing space-time diagrams, kind of like you see in special relativity, where one axis is like the position and the other axis is time. And so we have a little freedom to how we want to do this. When I learned it that the time was the vertical axis, so time went this way, upwards, that was time, and space went that way. So, reading something like this, with these as my axes, I would say, okay, maybe I put some arrows here. No, we don't even need the arrows. Let's not put the arrows yet. This would be B particle is moving along, comes here and hits C, at C, or I should say, at the vertex. That particle B disintegrates and becomes two particles. It becomes particle C and particle A. And they move on in time. Now, it turns out this is the opposite of the major standard we run today. And the major standard, which is what we're going to be following now, is that time goes from left to right, and space is the vertical axis. Okay? So if that's the case, now when I look at this picture, what this picture is telling me is there's a particle A and B, and they're moving along to the right. I'm drawing it to the right, but they're just moving along in space, in time, getting closer and closer as time goes on, until they reach this vertex, and at that vertex they collide with each other, they disintegrate, they annihilate, whatever you want to say, and they become particle C. So as you move from left to right, you're going through time, watching it happen. And I say the vertical axis is position, it's space, but don't think of it as literal, this is actually the position of the particle. It's more like, are the particles on top of each other? Have they collided? Or are they separate from each other? Okay, so don't put much stock into literal positioning in the x direction, in the vertical direction. Rather, it's just telling you kind of a representation of, are the particles close to each other or far away from each other? Are they moving away or coming closer? That's mostly what you have to worry about. But the most important thing is reading from left to right for time. Of course, this is a philosophical thing. If you ask people in different cultures and different professions, everybody will kind of think of time in different ways. You know, we, in the English language, when we read books, we read from left to right, top to bottom. We start at the top, move down to the bottom, but we always go from left to right. So we naturally think of time as progressing from left to right. But not all cultures do this. Some cultures read from right to left. Some cultures read top to bottom. And so different people have a different kind of visualization of time. But for particle physics, the standard that is generally used nowadays is time moves from left to right for these Feynman diagrams. Okay? So when you're reading something, that's why if you go back to this particular diagram, we had an electron, which is the top guy on the left, and a positron, the bottom guy on the left. As you move from left to right in time, they're getting closer and closer together till they reach this vertex right here. Then at that time, they collide, they annihilate, become a photon, and that photon then progresses in time, gets to this vertex where it decays into another electron and positron, and they go on their merry way. All right, so this is your basic vertex, and then what you can do with this vertex is you can always rotate it. So instead of having A and B turn into C, maybe you have something like, you can have B and C turning into A. B and C turning into A. There's nothing wrong with that. And you can just keep rotating these. And this is always true for all these kind of vertices. There's nothing wrong with rotating them. And in fact, you'll get different interactions sometimes, especially when we start to add these vertices together, these kind of puzzle pieces together to make more and more interactions. By rotating them, you can get some interesting things. For instance, I'll draw it over here so it's not as messy. We had this interaction. The electron and the positron come in, become a photon. That photon then disintegrates in an electron and a positron, right? Well, what if I did something like this instead? I have an electron and a positron, and I have a photon like this. So electron, maybe indeed, if I'm actually rotating this, so take this particular guy and rotate it clockwise by 90 degrees, what it becomes is E plus, E minus. This is my photon. E minus, E plus. Let's say, I'm sorry, E plus here. This is E plus, this is E minus here. Let's say it's E plus here, E plus here, E minus, like this. Let's say this were what I was drawing. What this would be interpreted as is a positron coming in, electron coming in, and then they kind of talk to each other with this photon. So maybe the positron sends a photon to the electron, and it receives it, and then they just go on their merry way. Now again, I'm drawing it so this positron and this electron are leaving each other, getting further away, but that's just for the neatness of the picture. Obviously, if this is actually a positron and electron, and they interact by the photon, they're going to get closer, because they're going to be attracted to each other. But you can see, if you take a particular Feynman diagram and rotate it, even though all the vertices are the same, you have the same number of particles, the implication, the inference you take from this is different. One, the first guy I'm circled, that's an electron and a positron annihilating, becoming a photon, that photon then creating an electron-positron pair. The one on the right is an electron and a positron interacting with each other, mediated by the photon, but not any annihilation or anything. They're just communicating. This is the Coulomb force over here. This is matter-antimatter interaction on the left. And all sorts of things can happen like this. Okay? So let's look at some of the rules we're going to need. By the way, it doesn't just have to be electrons. There's going to be a bunch of different particles, but it goes like this. Whenever you draw your Feynman diagram, you're going to have solid lines and not solid lines. So the solid lines, these are the particles that are going to be the fermions, okay? So you'll have a fermion. Let's say here's some fermion, here's some fermion, whatever they are, maybe electrons, maybe quarks, whatever, or even neutrinos. And then a non-fermion line. And a non-fermion line can come in different ways. You can have a wavy line. That's going to be a photon. You can have a kind of spirally line or a springy line. That's a gluon. And then the weak interaction stuff, it's not quite a standard yet. Some people just do the weak stuff, the W and Z bosons. They'll do like the photon. Other people make it a dashed line, and I'm going to try to stick with the dashed line convention. Dashed line convention will be the W plus, W minus, and Z bosons. Okay, so those are your mediators, they're called. Those are the bosons, those are the particles that allow these interactions to occur. Okay, so for instance here, we can have something like this. A nice basic vertex, puzzle piece, we say. The next thing you need, so you're always going to have 3 lines at a vertex. Okay, it doesn't have to be, well, you need 3 lines at the vertex, so you're going to have 2 particles interacting, mediated by a boson. Next thing you need, and remember, everything's time moving left to right. Next thing you need is the convention about the directionality of these particles. Sometimes the major reason we need this is for the calculations that are done later when we do integrals to figure out these the magnitudes of these things. However, another convention is it allows us to kind of differentiate between particles and antiparticles. So the convention goes like this. If what you have is a particle, particles, normal matter, so electron, proton, neutron, up quark, I should say, down quark, whatever, when they move through time, their arrow moves positive time. So a normal fermion, you would put a little arrow on the line, and that tells you this is a regular particle. It's a normal matter particle. If what you have is an antimatter fermion, and I'll show that by the little bar on top, maybe a positron or an anti-up quark, or an electron, anti-neutrino, whatever. If it's an antimatter version of a particle, the convention is to write the arrow going the other way. Okay? It can be a little confusing at first, because what it looks like, this is saying, if you don't think about time going from left to right, if you don't think about that, if you look at the picture, it kind of looks like you've got an F coming in, hits this vertex, sends out a particle, and then F goes out that way. Okay? But that's not what's happening. What this is saying is both particles are moving in time left to right. It's just that this F with the arrow going backwards is not a normal fermion, it's an antimatter version. Sometimes people like to philosophically think about this as saying an antimatter particle moving positive time, just moving along, is just like a regular particle, regular matter particle, moving backwards in time. So they're saying, when they think about it like this, let's say we take this particular picture here, you've got the electron coming in, and a positron coming in, you put it going this way. So one way of thinking about that, if we cut this off here, we only look at the left side over here, it kind of says that what we have is an electron moving forward in time and an electron moving backwards in time interact to create a photon. Okay? That's a very weird way of thinking about things, but a lot of times it can be kind of useful too. Now, whether that's actually true, whether a positron moving along is really an electron moving backwards in time, no, not really. No particles, as far as we're aware, unless you believe in things like tachyons, are actually moving backwards in time. But you can get some insight when you think about things, because there are particular symmetries in nature that deal with time's direction and things like this. And you get things like parity symmetry, or chiral symmetry, or time reverse symmetry. All this kind of stuff become very important when you're studying high-level particle physics, because it'll help tell you whether interactions are possible or not possible. But for now, just take it as a rule. If what you have is a regular matter particle, then the arrow that you put on its fermion line moves with time. And if you have an antimatter particle, its arrow on the line goes the opposite direction. And then when we go do the actual calculus, Feynman calculus of this kind of stuff, these backwards lines will be able to tell you about negative momentum versus positive momentum and all kinds of things like this. This is allowing us to conserve momentum. This is something we're going to have to worry about when we do the calculations. But these are the basic rules so far. You've got two fermions interact in some way. At some vertex, you have three interactions, or three particles interacting at a vertex. The mediator of the interaction is one of these three. It could be a photon, a gluon, or a WZ, or a W plus, W minus, or Z boson, depending on the nature of the interaction. If this is a Coulomb interaction, then of course it's a photon. If you're dealing with quarks, maybe something like beta decay, where you have a neutron turning into a proton, then that's going to be W. Or Z, weak interaction stuff. Or you could have the interaction of the quarks in a proton. Those interact by gluons. Or maybe you have one type of quark changing into a different type of quark. That's going to be a gluon interaction. Or maybe you have a gluon interaction between quarks where the quark doesn't change its type, but changes its color. We saw when we were dealing with the standard model that quarks had the three different colors, red, blue, and green. And what color the quark is matters when we're talking about whether you can create a particle out of these quarks or not. Other things we need to worry about is we have to conserve charge. We must conserve charge. And that's going to help us a lot when we deal with these W's and Z's, when we have weak interactions. Which one of these weak bosons do we use? Do we use the W plus or W minus? How do I know which boson I have to use here? Well, because the W's are charged, W plus means it's a positively charged W boson, then you would look at the vertex, you'd look at what particles are coming in, what are their total charge, and then what particle is coming out. And they better have the same charge, because you have to conserve charge at every vertex. So we're going to be using that a lot as a rule to figure out which particular interactions are legal, which are illegal, or here's a particular Feynman diagram, fill in what's missing, things like this. And then just as a hint, a tip, is if you see a neutrino, it must be a weak interaction. Okay? The only way you're going to have neutrinos in these Feynman diagrams is if the interaction was done by or mediated by one of the weak bosons. If it's a weak interaction, you can get neutrinos. If you have a neutrino there, you know the mediator can't be a photon and it can't be a gluon. Now, which of the W's or Z's it is, again, you look at the conservation of charge and things like this. Another thing to worry about, photons only interact with charged particles. So a photon can mediate something between gluons because gluons have charge. Or a photon can mediate something between leptons, like the electron or the muon, because they have charge. But a photon is not going to mediate something with a neutrino because neutrinos are uncharged, they're neutral. That's why neutrinos have to use the W, because gluons, they're only for quarks. Photons are only for charged particles. So the only thing left for a neutrino, which is an uncharged non-gluon, non-quark, is the weak interaction. Okay, so let's look at some examples and see if we can interpret what the heck is going on here. Let's try a nice complicated one. Let's say we want to do beta minus decay. Beta minus decay. Now, if you remember what beta decay is, beta minus specifically, that is when you have a neutron turning into a proton plus an electron antineutrino. Okay. Let's make sure from the nuclear level, nuclear physics level, that this reaction is possible. You have a neutron, neutral, so no charge. Proton is positively charged, electron is negatively charged, and neutrino has no charge. So at least by conservation of charge, this is perfectly possible. And of course, by conservation of energy, conservation of mass, let's say, the neutron is a little bit bigger than a proton, a little bit more massive. Electrons are very, very tiny, and neutrinos are almost zero mass, so they're basically irrelevant in terms of mass. So yes, a neutron can indeed naturally decay into a proton, an electron, and an antineutrino. So this is possible. It's an interaction that occurs. Now, how would I write the Feynman diagram for such a particular interaction? Well, the problem with this guy is the neutron and the proton are not themselves fundamental particles. Now, I could draw the Feynman diagram assuming they're fundamental particles, but I'm not going to get a lot of the detail involved with what's really going on. So instead, what I have to do is I have to kind of open up the neutron and open up the proton to see what's inside of them, what are the fundamental particles that make them up, and then I'm going to work with those guys instead. So if you remember what a neutron is a set of 3 quarks, and those 3 quarks are two downs and an up, right? Up, a down, and a down quark. A proton is also a set of 3 quarks, but this time it's 2 ups and a down. Okay? And of course the electron, that is a fundamental particle, so there's nothing more I need to worry about for him. And the neutrino and the antineutrino, they are fundamental particles too, so I don't have to open them up. So now I know what I have. I've got 3 quarks, an up and 2 downs, turning into 3 quarks, 2 ups and a down, plus an electron, plus an antineutrino. So now I need to draw this Feynman diagram. And what's helpful here is if you do something like this, make a bracket, and we say, okay, here's a neutron, and that neutron is, let's say, up, a down, and a down. And they have their little lines, their fermion lines, going along in time. The up's going along. I'm going to make the assumption that this up just carries along, keeps going, does not change. He's an up, he stays an up, nothing happens with him. I'm going to assume this down is just this down sitting here. That down nothing happened to him, he didn't change, he just stayed in a down. What did change, however, was this down quark changed into this up quark. Okay, so that's the guy that's going to be changing here. That's why I'm saying this first up, he just continues along, this down continues along, and these things are going to become an up, a down, and an up. Okay? Now, of course, it's up, up, down the way I wrote it there, but the ordering of which of the 3 quarks goes first is completely immaterial. So the up became an up, nothing happened. Down just became the down, nothing happened with him. Now what I need is a Feynman diagram which changes a down quark into an up quark. Okay? So this is where the diagram comes in. So here's his bracket there. All right, so the interesting part I'm going to do in blue here, and that goes like this. And I'm sorry for all the little dashes all over this stupid thing. I don't have my my little glove to protect the screen from my hand, to recognize in my hand. So this down, I'm going to kind of draw it angled so it'll give me a little bit of room here. But again, the vertical axis being the positional axis, there's nothing really true about the fact that the up just went straight, but this down is going down at an angle like this. You know, that doesn't mean this down kind of went away from the other 2 guys. It's just I'm moving it to give me some room to make this particular drawing. So this down goes down here. Notice these are all regular particles, regular matter, so all the arrows are pointing with positive time. And here is going to be my vertex. So this down is going to change. It's going to decay, and the products are going to be the up quark. So now I've gotten my up. That's exactly what I needed. However, remember, you always need 3 lines. 3 particles interact at a vertex. And so I'm going to get the mediator now. One of the bosons is going to be responsible for this particular interaction. Now, I don't know which boson it is yet, so I need to investigate further what's going to happen. What else do I know I'm getting out? So far, all I've gotten is the neutron has become my proton, but remember, I still need the electron and the antineutrino. They're still sitting out there waiting. So I know there's going to be some electron over here, and there's going to be the antineutrino in electron version. So they're still waiting to be produced. So whichever mediator is changing my down quark into my up quark, whatever boson does that, it has to itself decay into the electron and the antineutrino. Okay? So something's going to come down here, and in that thing is going to become these 2 things. However, what I don't know is which boson it is. And because I've already limited myself to how I draw them, depending on which one it is, that's why a lot of people don't like the dashed thing for the W or the weak stuff. Because if they just make it the same drawing as the photon squiggly line thing, then they could just draw the squiggly line and then later on write in which of the particles it is. Whereas now I can't draw it until I know, is it the photon or the W? However, this is very easy. We already know what it is, because I already said if you ever see a neutrino as one of the particles of the interaction, then you know it has to be a weak interaction. So it has to be either a W or a Z boson. So okay, so that means this must be a weak interaction, and so I get my dashed lines. There's the weak interaction. Whichever one of the weak interaction bosons this is, it's going to decay into the electron and into the electron antineutrino, and because he's an antineutrino, I put his arrow backwards in time. Okay. So remember, it's kind of weird, but when you have an antimatter particle, his arrow has to be reverse time, even though he's moving forward in time. So this is not saying this is an electron antineutrino moving backwards in time. Even though the arrow I put on him says or shows it as backwards, really, this is an electron antineutrino moving forward in time, and to represent it, you do a backwards arrow. Kind of confusing at first, but you get used to it. The last thing I have to worry about is which one of the 3 weak bosons do I put here? It's going to be either W plus, W minus, or the neutral Z. And the way I figure it out is I look at conservation of charge. I say, okay, what was happening here? Notice I started with, at this point here, at this particular vertex, I started with a down quark whose charge is minus 1/3. And what I got out was an up quark whose charge is positive 2/3. So at this vertex interaction, or at this interaction vertex, I went from a charge of negative 1/3 to a charge of positive 2/3. So I gained plus 1 charge. But that's bad. You don't want to gain charge. You need to conserve charge. So in order to conserve the charge, whatever this third particle, this boson is, it has to make up the difference. And since the difference was I gained positive 1 charge, then this boson better have negative 1 charge. So that when you add up the 2, you get a total neutral. Because every vertex has to be neutral, coming in to going out. If you had plus 1 charge coming in, you better have plus 1 charge going out. And if you don't, then you need to have one of your particles take that charge with it. So I had negative 1/3 coming in, positive 2/3 going out. That means I have an extra 1 charge. So this particular W better be the W minus. And now let's make sure this makes sense. Let's look at this vertex, because we still have to conserve charge here too. We start with a W minus, that is, he's got a charge of -1, gets to this vertex and goes away. So I've lost my -1, so I better come up with the -1 on the other side, right? I came in with -1, I have to go out with -1. Well, the neutrino, the antineutrino, has no charge. But the electron does indeed have a charge of -1. So we're all good. We started with -1/3, gained plus 2/3, but this W minus over here, going down this way, took with it -1 charge. So at the yellow vertex, charge is conserved. If you add the left and the right together, you get the same amount. Then at the green vertex, you have a charge of -1 coming in. So coming out of it, when you add up all those particles, you better still have a charge of -1, and indeed we do because of this electron. And now we look at, does this match the decay process I was talking about? Well, we started with a neutron. What do we end up with? We have a proton plus an electron antineutrino. And that's exactly what we want up here. And so this is the basic decay Feynman diagram for the beta decay. And this is basically how you're going to go about either creating your own Feynman diagrams, drawing it out like this. Someone gives you a particular process and you need to write it down, or someone gives you a Feynman diagram and you look at it, you study it, and you find out, is this a legal process or will this never happen? And so the rules you have to look at are, number one, do the mediators match the interactions? So for instance, if I had said this was a photon here instead of a W, and you have no idea what the rules are, well, you look at the beginning, you started with a neutron, you look at the end, you get a proton, electron, and antineutrino with a mediator involved. How do you know that's not right? It looks fine, but then when you start looking at the details, a few things pop up. Number one, look at the conservation of charge. You know this can't be a photon because on the left, coming into the vertex, you have a total charge of -1/3. And on the outgoing, you have a total charge of 0 from the photon plus 2/3 from the up quark. So you have a charge of plus 2/3 on the outgoing. Well, -1/3 coming in, positive 2/3 going out, you didn't conserve charge. So automatically you know that can't be right. On top of it, if this were true, then you'd have a photon interacting with a neutrino. But a neutrino is neutral, and you know neutral particles do not interact with photons in this way. So that's the second reason why you know that could not be possible. And of course you can make the same types of arguments for how do you know that's not the W plus or the Z or the gluon or whatever. You have to look at these interactions and study them. Sometimes they're really easy to tell, oh yeah, that can't be right. Sometimes they're not quite so easy. Sometimes there's a little bit of a trick involved, or sometimes the problem is kind of a minute problem. But for the most part, especially at the level we're discussing these things, this is pretty easy. The rules are very easy. You could give this to a child, tell them the rules, don't give them any of the details. Just say, follow these particular rules. The arrow comes in, you add up these numbers. The arrow goes out, you add up these numbers. Do they match? If they don't match, what do you have to add in there to get them to match? That's conservation of charge. Things like this. It's very, very nice. That's what makes this such a powerful, powerful thing. The fact that Richard Feynman was able to invent this, to kind of visualize this out of the mathematics involved, is unbelievable to me. Because it takes something so extraordinarily complicated as an infinite series of integrals each integral itself is not necessarily going to be that easy. And you have to think of every possible way an interaction could possibly occur. Add all those things up. He's able to take that kind of thought, that mathematics, and say, I could think of it like these little pictures, these little toys, these puzzle pieces. Put them together. There's very, very little complexity in that. All you're doing is thinking of different ways things can happen. Can I add an extra line here? If I add an extra line here, what line could it possibly be? I don't even have to think about what it actually means in terms of a description. Like, if I put an extra photon here, that means, for instance, why couldn't I put a photon right here? Of course I can. There's nothing stopping me from doing that. That's a gamma there. Is that legal? Sure, it's legal. What I have is an up quark coming in to this vertex. Positive 2/3 comes in, positive 2/3 goes out, and a photon is neutral, so conservation of charge is fine. Up quarks, they're charged, so they can interact with the photon. The photon itself interacts with the electron. The electron is charged, that's fine. The electron has a charge of -1 coming in, -1 going out. So yeah, nothing breaks the rules, and this is a possible valid interaction. So if I'm actually going to try to calculate the probability that something like this occurs, that's one of the extra things I got to worry about. But look how easy it is to just stick one of those extra things in there without having to think about, okay, what does this actually mean? Oh, this is a Coulomb force of attraction between an up quark and an electron. Is that, how likely is that to occur? Well, the mathematics behind these pictures would tell me. Maybe it's very unlikely this occurs. Maybe it's very likely. I don't know. But to be able to have it as a possibility is very easy just by thinking about the pictures. So that's it. That's your introduction to these Feynman diagrams. Obviously, there's billions and billions of them you could draw out and you could try to look at. Some are super, super complicated. Some are very, very simplified. But if you think about the rules, then this stuff tends to be quite straightforward. Next time we'll do some more examples. But I think if you could do this particular example, then any other example is going to be on par with this. Okay? And then, of course, we'll start looking at how to interpret the diagram mathematically. What does this mean? And what we're going to find is every time you see a vertex, that vertex, you're going to start with an integral. You're going to say, okay, what do I have? Well, I've got these fermions, so you have terms for the fermions. I've got this many vertex. Each vertex, I get an extra factor of something up in there. And then I have for each momentum, each one of these little arrows of time, I'm going to get a d for blah, blah, blah. I'm going to have deltas, all sorts of stuff in its big old long integral. But you don't even have to think what each piece means. All you have to do is know, okay, here's a set of rules. If you see a vertex, write down this little term. If you see a mediating particle in between, you write down this term, depending on which particle it is. If you see a forward-facing arrow, then this momentum term is going to be positive. If you have a left forward-facing arrow, then it's going to be a negative momentum. We're going to conserve momentum. That's what the delta function is going to give us. And all sorts of stuff. There's going to be a list of rules that says, when you look at the picture, do you see these items? For each one of these items you see, write it down in the integral. Once you wrote all that stuff down, now you do the integral, and you get your answer. So that's going to be the point of the actual calculations involved with this stuff. But for now, at least, you should be able to look at a Feynman diagram, tell, okay, the arrows of time, arrows of time should go this way. You should be able to look, say, okay, I know time goes this way, so this guy, what is this telling me? This is a Coulomb force interaction. What is this guy over here? There's electron-positron pair coming in and annihilating, so this is matter-antimatter annihilation. I look at this guy, I say, okay, You have a neutron turns into a proton, electron, antineutrino by the mediation with a W minus boson. So this is beta minus decay. Okay? You should be able to look at these things and just tell from what's going on conceptually what it means. Later on, we'll worry about the mathematics. Anyway, hope this is helpful, and I will see you next time.